So today is our last lecture, right? And it's going to be on memory. But I initially had hoped to cover more areas, but I think this is a good place to stop in terms of I think we've gone through a lot of things in this course, um, and memory is an interesting and very complex topic. Um, there is a lot to it. We're not going to do justice in like an hour or so that we have here. But I'll just introduce you to some concept in there, and some of you I'm sure have picked topics that are related to memory and how memory forms. Um, so um, a lot of discussions of memory start with a graph like this, and it's it's the whole idea of with any scientific field, you really want to divide and conquer in some ways. You want to have meaningful division where a topic becomes manageable. Now, those divisions, we talked about them in the past, right? Let's say we talked about different brain areas that are involved in processing visual information. We said, yes, there are some divisions of labor, but all of this happens in an integrated system. There is not an obvious difference sometimes among these different things, and a lot of them are graded. So keep that in mind. We're going to go through every box here just so you're familiar with terminology. There is the first division that you see here, the big one, is between what we call long-term memory and sensory memory, short-term memory, or working memory. You already have some intuition of what that may mean, right? So a lot of us like kind of experience a division between things that we're working with at the time, but do not retain in the long run. And that's the division. The book provides some, and I'm going to go through some more of these things. This is a very simplified way of thinking about how these two main divisions that we talked about here relate to one another. Which is you're saying about the sensory input comes in, and it could be a sound or something else. For example, if you're talking to someone on the phone and you ask them their PIN number or something, and you want to write it down, you have to attend to what they're saying, right? And that goes into your short-term memory until you write it down. So what are the stages in that process that I just described? Well, another example, let's say you have a double authentication and you get a text message with a number, right? Initially, when you look at it, that's sensory register. There's a register that you look at it, right? It's the same when somebody reads out the PIN to you. When they read out the PIN number to you, you have a sensory register. You could probably repeat that, right away. Attending to that information would give you short-term storage. In your short-term storage, you're repeating these numbers, right? If it's a 4-number PIN, you probably can do that. And then after many use of your PIN, after many rehearsals, that PIN becomes part of your long-term memory, right? So do you see these stages, how it would play out in like a simple example, how it would be sensory register, which is like the initial thing. So another example of sensory register is that, let's say you're not even paying attention to someone and they say something, and then they're saying, oh, you weren't paying attention to me. And then you're able to repeat that right away, right? You've all experienced something like this. That information that you didn't even attend to, but exists in some sensory area, that's sensory register. But when you attend to it, then it becomes part of your short-term memory, and you could rehearse it until it becomes long-term memory. So the book says, well, sensory memory is really milliseconds to seconds. It's something that primarily decays. So it fades away very quickly. The capacity of it is fairly high in a sense that sometimes you could look at a whole image and have some sensory information about that image of every part of that image, right? You could flash an image, it could go down, and then people could ask you questions about it. So this sorts of the capacity for something like that is really high. You could keep it in your sensory information. Short-term or working memory, and these two terms are being used interchangeably a lot of times. This is around seconds to minutes, where you could actually you could actually keep something in your mind in a working memory style, like a number that you're trying to memorize. Now we talk about why they say it's limited to a certain number of items, but people, there's a magical number 7, like 7 plus minus 2 items that you could keep in your mind. Well, I'll show you an experiment of how people try to find out what that number is. Are you consciously aware of it? Yes. How do you lose it? Well, interference. So let's take the example of somebody gives you a pin or a phone number, and then you try to write it down. Anything that happens in that window, it's going to distract you to a point that you're going to lose the number, right? So that's what we call interference, and I'll talk about it more. But also it could decay, right? So as you have to find a piece of paper or something to write it down because it's decaying out of your working memory. Now we talk about the other examples a little bit. So the process of working memory is before you actually write it down, right? Or type it or make a, I was just using that example of this period of time where you're maintaining some information in your head and until you have an opportunity to write it down. So that window of time is short-term memory. Because if you do not write it down, it's going to be lost, right? So you're going to completely lose that phone number. I feel that way with names. Like when somebody tells me their name, about like 5 seconds later, I've completely forgotten, right? It's just gone. And that's like just maintain it in short-term memory for a very short amount of time, and then it's gone. So that's what I'm talking about when we're talking about working memory. It's the memory that you have when you're actually maintaining something, or when you're doing some arithmetics, right? If I say, what's the sum of 23 and 46? So some of you, would do that in your head and think about, okay, what is that process? You could do it up to a certain number, right? Because you have to maintain all the residuals and add them up, and you wouldn't be able to do that if the number is too long. So this dissociation between, let's say, what we call short-term memory or working memory and what we call long-term memory, you could establish that in many different ways. You could establish that through some physiological stuff, right? So brain trauma, or for example, if someone tries to use their working memory to remember something, if you give them some shock, right, in this case electroconvulsive shock, or TMS that we talked about, it interferes with their ability to maintain that information. But that doesn't interfere with what we call long-term memory. Or let me give you some overview of long-term memory before I say that. Okay, so long-term memory, and again, this is divided into non-declarative and declarative. I'll talk about what they are. But this is the memory that you could recall, you could remember minutes or even years from now, right? You have an experience, and that experience leaves a memory trace where you could recall a long time from now, be it a few minutes from now or a face that you'll see a year from now. Someone you met in this class, a year from now, you see that face and then you recognize it. And I'll talk about a case of interference for it, but just have that much background of what that means. Okay, so there are different ways to think about the differences between short-term memory and long-term memory. And there are different ways to establish the differences. But these are a few of them that you could think about. And as I said, the book had time course, capacity, conscious awareness, and the mechanism of loss. But think of it along these dimensions too. Basically, duration, right? This is another way of saying how long you can maintain it. It's short versus long. Capacity, low versus high, for working versus long term. Coding, which is a lot of working memory information or surface information, but the long-term stuff have mostly meaning attached to them. Forgetting, like it's easy and quick to, fast to forget working memory stuff, but really slow and kind of stable with long-term memory. So I'm just using this as a different way of, a terminology for what this means. And this is a terminology that psychology people mostly use. So the thing about working memory, the most interesting thing about working memory is this capacity idea, right? That we have a capacity of 7 plus minus 2. Some people say 4 plus, 4 to 5. But it also depends on the content, right? If they're really long words, then the capacity would be smaller. So it's not quite as obvious of, okay, these are slots that you have, like a computer slots, and then you attach an item to each of them, and then you keep them in working memory. It's more of a complicated story of capacity. And also there is the capacity for nonsensical words that have no meaning to you is much smaller, meaning that you cannot, in your short-term memory, it's much easier for you to maintain 5 words that have some meaning than 5 words that have no meaning to you, that are in a foreign language or something like that. So it's not, I just want to contextualize the idea of 7 plus minus 2 is not as obvious. I'll show you an example experiment that people use to, I can't find a better display of it with someone's face not being at the bottom, but imagine the task is something like that. A lot of working memory tasks are like this. You get a display of some images of some colored patches. You have a certain retention interval, and then you have a probe. This is basically a change detection task. You're saying, has something changed in this image or not? In this case, it looks like this square changed to this one. So now you could see that, well, you can manipulate the number of objects in this image. And if you manipulate the number of objects, you could see up to how many they can actually retain in their working memory and be able to answer that question. Let's see a few example trials of this. Okay. So display will come up, and then we have an interval, and then the probe display comes up, and then you have to see if something changed or not. I don't know the exact timing of this, but let's give it a second. Okay. So let's do it again. So did something change? Yes. It was the bottom right one. Another trial. Did something change? No change. But you can see if even going from 4 to 6, it becomes much harder, right? Something changed? Yeah? Which one was it? The yellow. So you could do this with different number of objects and different color combination. And then eventually you could look at, let's do another trial. Yeah, right. So in this case, you have 9 items, and that's really hard. But there was a change. So you could basically, when you do that, you could actually look at your set size. And we talked about the concept of set size, which is usually, in these experiments, is usually the number of objects. We talked about it in the context of visual set. You could look at the set size and then the percent correct. And as you would expect, you get this decay, right? As the number of objects increases, it becomes harder and harder to maintain all of them and to be able to answer whether one of them changed or not. So your attention is likely to go to one of them. If it was like an attention effect, it would not even work like that, right? You would show a lot more decay if you could only look at one of them. It's just that you're trying to maintain all of them in your working memory and then answer. And you could see up to 4 seems pretty good. And then when you go above that, there's a big decay in performance. So these are the type of experiments people run to measure the capacity of working memory. Now, there are other versions of it where they also give you another task. Like, they'll give you another task of, is there a motion sensor? Yeah, thanks. It looks like. Thanks, Olivia. Thank you. So there are tasks similar to this one, but they also have another thing to do, right? So you maintain something in working memory. Like here in the delay period, you weren't doing anything. But sometimes in the delay period, they might give you an addition, like say, okay, add 5 and 6 and see what the number is. So they give you another task, and then they measure if you still maintain something in the memory. So just those are different paradigms people use for working memory. But this is the type of paradigm that people study short-term memory with. And this is the like a few second window that they're really interested in. Can you maintain them or not? So these were colored squares, but you could imagine you could do a similar experiment with numbers or with letters in the English alphabet, or where you're saying, okay, these are the few letters, remember these, do another task, then tell me what the letters were. So you can imagine something like that. So that's how this capacity limit comes into play. It's basically how many of these items you could retain. Now, in your experience, like I always feel that with the double authentication, how long should that code be for you to look at it once, maintain it in working memory, and type it? What is your limit, in your opinion, in terms of the number of digits you can maintain? 6 digits, right? I have a hard time with, personally, I'm talking, like, I have to look back. Like, if it's 4 digits, I could do it. But if it goes above that, I have to look back at the number, right? It's like.
But if you say it aloud, and if you have a job where you have to memorize ID numbers, that's how you remember it.
Okay.
You say it aloud.
In the workplace?
Yeah.
Okay.
Well, not, yeah.
Yeah. But I'm saying, like, we also experience these sorts of limits even in everyday life in terms of how many digits can you actually remember, right? Now, again, there are ways to get around it. You have a question? There are ways to get around it in terms of you could try to make smaller groups, right? That's what groups are. So you're saying instead of maintaining 9 separate digits, which my brain, my working memory doesn't have the capacity for, I'm going to remember 3 smaller sets of 3-digit numbers. So if you could give some meaning like 500, 625, something else, then you're basically chunking it. So your working memory can basically, you're giving a smaller chunk that is meaningful to each of those slots. So that's what chunking is. Yeah. We'll talk about it. Yeah. So we'll get to the brain areas. I just wanted you to have some background in terms of what are we talking about when we talk about different memory systems, and then we'll talk about brain areas in like 2 slides or something. So that's one distinction, and I hope you have some idea of what that means, at least in terms of when people talk about working memory or short-term memory versus what we're going to talk about long-term memory. Now, long-term memory itself branches off two major areas. One of them is declarative memory or explicit memory, and non-declarative and implicit memory. All right, so what are the differences? The difference is that first, declarative, what can be declared, or explicit, they mean the same thing. It's explicit. Non-declarative, what cannot be spoken of in some ways, and implicit mean the same thing. So what is explicit memory? Well, this is the type of memory that you have that you consciously can access them and you could verbalize them. Examples, again, two categories: semantic memory and episodic memory. What is semantic memory? Well, these are word knowledge that you have about what color is this sky. Dogs are pets. I have a few examples, like this car is more expensive than that car, or that what day is my class, right? All of these things are semantic, declarative knowledge that you could verbalize and you have knowledge of the world about them. Also, explicit are episodic memories, right? You could imagine your commute today, right? You could kind of do a mental travel through your commute today. Okay, I got out of my house, I got on the Q train, and then I came up, and right, you could have that mental imagery and episodic memory of those incidents, right? Okay, where did you pick up lunch? What did you pick up? Like, how did you pay? Do you remember the moment you paid? What was your method of payment? All of these information falls under episodic memory. You have episodes in your head, and you could verbalize them. You could actually access that information and verbalize them, talk about it. In contrast to explicit memory is implicit memory. This is the type of memory that you cannot really verbalize, or and it's also called procedural memory in a lot of time. But we'll see. So there are different categories here too. But you think about what is a memory that you have that you cannot verbalize, right? Examples of this would be classical conditioning. So sometimes, again, we do this a lot with, animal experiments where you have, for example, fear conditioning. A fear conditioning is a sound plays, for example, or an odor is in the environment, and the rat or a mice in a cage, in a metal cage, and they're shocked. Like you just deliver a shock to them. And they would forever remember that smell associated with the shock, right? That's just that they just make that association. These are conditioning experiments, right? We also have those experiences where we associate a certain smell with a good outcome, or certain smell or something, maybe with maybe we have a experience of fear when we smell something. So these are conditioning, but we don't really know. They're associated, but we don't really know. We can't really verbalize them or something like that. It's just a matter of, it's a type of memory where associate different stuff together. Another example is perceptual learning, right? When sometimes, the example of an accent is a good example. People have different accents, and a lot of time happens that you're not able to understand someone, a new friend or something, or you're learning a new language, and then you learn it in a certain accent, and then a new accent seems so different from it. But after a short amount of time, you kind of pick it up. You kind of pick up, okay, this is the mapping from this accent. And it's kind of this is kind of a perceptual learning that you do. This is also the kind of memory that you do when you learn a skill, right? Driving or typing. A lot of us can now type on our computers without thinking about it, right? So you just have a memory of, okay, this word is this pattern of finger movement. Or another, skilled job like driving in Formula One, or you don't have time to think about those things. These are procedural memory. These are just skill memory, right? You just have done it so many times that starting from it, you just know how to respond. and you don't really have conscious access to it, right? If you drive, you'll have experienced something like this where you you somehow find yourself becoming suddenly conscious, and you've passed like a few blocks, and you've gone through multiple red, like the right way. And I'm not saying basically you've done everything right without having any conscious memory of what you've done. And that's sort of a skill and procedural memory. Does that make sense to everyone? You all have that experience of doing something right without having like it happens with cooking. It happens with a lot of the skill that when you've done it a lot of times, you could actually unconsciously do it. And that's why uh, initially when you see this um, in a long-term non-declarative memory, which is the type of memory that I was just describing, it's saying, are you consciously aware of it? Not really. Meaning that a lot of those memories, a lot of those actions you're doing it like, let's say, I guess you're folding laundry and listening to something. Your attention is with what you're listening, but you're able to go through the motion without being conscious of. That's what that means. Questions about these? You all have a good intuition of what these categorization is? So, let's see. Yeah, so we initially started from this division, right? We talked about these divisions. Under declarative memory or explicit memory, there are events or episodic memory, that these are episodes that are in your head of your life experience. Some of them are new, some of them are old. You have episodes of maybe your childhood home or your elementary school or something like that. And facts that are semantic memory that we just talked about. These are world knowledge. So events would be a specific personal experience from a particular time and a space, and events usually have a time and a place stamp. Sometimes you may remember something but not know exactly where and when it happened. That's also possible. Facts are world knowledge, object knowledge, language knowledge, conceptual priming. Non-declarative memory, as we saw, these are procedural memory, um, perceptual representation system, classical conditioning, and non-associative learning. And these are, I didn't mention these, but these are habituation, and these like sense, yeah. It's like when your body habituates to something, or your brain habituates to something, it response changes to an input, and based. So what is the broadest definition of memory? Well, the broadest definition of memory is that the system's response changes if they have interacted with this before. Does that make sense to everyone? Like there's when the system interacted with something, it changed the system in a way that the next time it responds would not be the same. And that's the broadest definition of memory. So if you are in an environment and it's always very loud, and you become less sensitive to loud sound, this is your memory. This is in your memory now. Meaning that because of your exposure to that sound, your brain has changed. And everything that changes the brain broadly falls under the definition of memory. That's what I'm trying to say. That's the idea. Yeah, and there are different brain areas that are involved in all of these different types of memory. We'll talk a lot about medial temporal lobe, and the involvement of the cortex in that area. Talk a little about basal ganglia, perceptual and association network, cerebellum, and the reflex pathway. All right. So before we talk about the brain areas, there is also this terminology that is good that you know about, where when we encode memory, like think of it of declarative memory, like a word knowledge or something. There's first a stage of encoding. So you have to encode this memory, right? You gather something new, you have to first encode it. And that also has two stages. The stage of acquisition that you acquire a new knowledge, and the stage of consolidation where you consolidate that memory, right? So, and that requires a lot of attention, right? You have to attend to something in order to basically, acquire that knowledge and then consolidate it. Then there's this storage where this memory has to be stored somewhere in the brain. And we talked about this before. Where are memories stored? Where are memories stored in the brain? Hippocampus? Well, I meant in the more generally, where our memories is stored. That's one area of the brain that is involved in memory formation. So I think I talked about this a lot in the first module. I said there are only like two types of things that happen in the brain, like two types of there. I don't know how to describe it, but there are, like I was saying, in the brain, it's a network, right? And a network really has units in it that are connected. So when you have units that are connected, there are two things that you could really think about in that system. What are those two things? The activity of the units and the connection between the units. But those are the only two things. And we talked about it in the context of the neural networks and artificial neural networks. And we talked about all the knowledge that we have. These got to be stored where? All the long-term memory that we have, where would that be stored? Where would it be? I just gave you two options. Well, which one of them would be? What's that? I said a brain is a network with units in it. The units are connected, right?
Cell body or event or
it would be in the connections, right? It would be in the connections. So if brain, like you've forgotten everything we talked about in the beginning, but so if we have a network of units and these units are connected to each other, like they are in the brain, the knowledge, the world knowledge, the memory, everything that the system has learned would be in the connections. That's how an artificial neural network works too, right? This all the information that this network has is between those connections. The units are connected. The connection weights define what knowledge there is in that system. It's no different in the brain. So a memory, a long-term memory in the brain is a trace. A trace is multiple connected units together. So the connections between the units define that memory state. Does that make sense? So there's no other place like to store it. If you have units that are connected, then you have like a neural network, like an artificial neural network. All the memory of the system, all the knowledge of the system, all the learning of the system has to be stored in these connections. And it's the same in the brain. Now, when we talk about working memory is maintained how? In the activity of the units. It's not necessary, it doesn't necessarily plants traces in a way where it changes the connections between the weight permanently. And that's what that means when people say memory trace. It's basically a permanent change of connection strengths between units. It doesn't leave traces in that sense unless you rehearse it to a point where you retain it in your long-term memory. But if it's only a short-term memory, it would be maintained in the activation, practically.
That's the concept of neuroplasticity.
Yeah, so the change, neuroplasticity just means that the connection rates between the cells change. And new connections could be formed between the cells. So in a neural network, a lot of times you have all the connections, and those connection rates change with learning. in the brain, you could also have new units be born, right? In hippocampus, we always, if you have a healthy lifestyle, if you work out, you could always generate new cells in your hippocampus and other brain areas, so you could form new connections. And that's what neuroplasticity is. Plasticity, the connections are plastic. They could change with learning. That's all that means. Okay, so brain areas. I'll go through some of these areas in more details, but this is an overview of the brain areas that are involved in these different types of memories that we just talked about. So here, non-declarative memories are shown in bluish, and declarative memories are in this orangish color. So with non-declarative memories, a lot of procedural skills, like how to swing a golf club, right? This is something, or how to play any sports. You have to acquire a lot of procedural skills in order to do that, right? You have to do it so many times, like if you play baseball or something, how you swing a bat, depending on the pitch you get, like that's a procedural memory. And a lot of those are in the cerebellum, which we have not really talked about in this course, which is in the back of the brain. It's below the cortex, and also in the motor areas and premotor areas, as you can imagine. Classical conditioning, fear memory, people hypothesize that a lot of things, these associations are made in the cerebellum. Habituation and priming, or the power of suggestions. Oh, sorry. Habituation is, people believe that it's a more of a low-level thing, that the brain is STEM. It doesn't really come so far up to your conscious experience of cortical experience or your central nervous system. It's more of a low-level brain STEM kind of thing that you habituate to things. Priming, I didn't talk about priming much. I'll get to it. But when you talk about episodic and semantic memory, now here we'll talk about this area a lot more, which is the medial temporal lobe, including hippocampus and amygdala and parts of the cortex, which we briefly talked about, like the parahippocampal area. All of those things are involved in forming these sorts of memories. Now, the memories are formed using these areas, but they're not necessarily stored in those areas. Like the memories could be stored back in the cortex, but you need hippocampus in order to form those memories, in order to kind of bind a lot of these memories to a place and a moment, in order for you to be later kind of recall them. Priming, or the power of suggestion, is the idea where sometimes we associate things together. And for example, in animal studies, you could just associate like a pair that always goes together. And then if you show one of them, the animal is primed for the second one. So they're kind of, if they always see two objects together, if you always see two friends together, you see one of them, the immediate thought you have is that where is the other one? And that's kind of what priming is. It's the idea that you're seeing one object primes you to select the other object better. And that is also a kind of memory, right? So I was saying, think of memory as this broad concept where it changes the response of the system because of exposure. And that leaves a memory. That's what a memory is. You basically, okay. So different, as I was saying, different brain areas, depending on the type of memory. Again, this is just a different display of a similar thing. Is basically these various regions are involved in memory formation. We're not going to talk that much about them, but I have this slide because after this, we're going to focus on the hippocampus and the medial temporal lobe. But I just wanted to show you this before we do that. So, for example, a lot of the aversive learning, right? The this source of a negative association that, well, this is a dangerous situation and I should not be getting into it. Amygdala is involved in a lot of those emotional learning. As I was saying, if you have a procedural, for example, a reinforcement learning task where you do a task the right way, you get a reward. And then you do it again and you don't get a reward. If you do it again, you get a reward. Then over many, many trials, the animal learns, okay, this is what I'm supposed to do, right? Almost every neurophysiology experiment starts with about 3-4 months, sometimes longer duration of animal training through reinforcement learning, right? The monkey is not like used to sitting in front of a screen and answering questions, right? So they have to go through a long period of training in order to be able to do that. And a lot of those things are done through basal ganglia. Cerebellum is for error-based predictive learning and conditioning. Again, this is the classical conditioning stuff and associative learning that we talked about. But you don't have to worry about these things. I just wanted to mention these areas because they're important. But we will focus on the hippocampus for the rest of the lecture. But let's take a 10-minute break and then we'll come back. So we're going to spend some time talking about the medial temporal lobe. This is an area that is very important for memory formations, and we'll see 2 lesion-based studies on why it is. But just for you to have an idea, medial temporal lobe is really close to the center of the brain. And on the right, you could see where hippocampus, which is the main area in medial temporal lobe for memory formation is. And you could see it's kind of deep in the brain. It's not part of the cortex. But there's an important cortical area, which is the parahippocampal cortex, that feeds a lot of inputs to the hippocampus. You remember where we saw parahippocampal cortex? What area? FFA? Yes, it's close. But what is this area that we saw? It's in the parahippocampal. What is an area that you know that is in this part of the? Is that? No. It's a parahippocampal place area that you saw in the context of what? Where did you see that area? Yeah, so when we were looked at object-based attention, we looked at 2 different areas. We said, okay, look at FFA, look at PPA, and see which one would be more active depending on what you're attending to. So this area does a lot of place and scene processing, and that's important for memory formation. So a lot of input from this area, from the temporal lobe, right, feeds into hippocampus. Not exactly, no. There are overlaps and everything with amygdala and everything, but not exactly. So what do we know about hippocampus? Just a few little things. It's shaped like a seahorse, and that's where the name comes from. As I said, it gets a lot of inputs from the parahippocampal cortex, and I mentioned this because we're going to look at an experiment. And it's really important for forming long-term memories. But it doesn't, if you lose your hippocampus and the surrounding area, you would still have a lot of older memories. And these were established, right? The importance of hippocampus and the medial temporal lobe was established early on by a lesion study. I mean, this is kind of the case for a lot of the studies and areas that we looked at. So the patient HM, he had seizures, and a lot of times seizures come from the temporal area. This is like very common thing, but people when back in the day, well, they didn't know. In this patient, they went ahead and removed both of them, like the uh, the area that includes hippocampus and the surrounding area. And what happened was that this person, like again, the seizure stopped, so that's a good thing, but it also started having a lot more other symptoms, including amnesia. And amnesia in this case being he was just not able to form new memories, new declarative memories. An example of it would be like a nurse would walk in, he would be able to talk to a nurse, he would hold a conversation, and then if the nurse went out and then 10 minutes later she came back or he came back, the HM would not know who they are. They would have to introduce themselves again. Right? So this is like I knew someone who done some experiments with HM. So so this surgery was done, I think, in the early 50s. And he became a celebrity subject over, decades. Like many generations of memory scientists built a career out of HM. But yeah, he had his medial temporal lobe. And so I mean, looking at this, you kind of know this is a view of the brain from below, right? And this is the front, this is the back. And these are different cuts, like A, B, C, D are different cuts of the brain for you to see, because this is a deep area, it's not on the surface. In order for you to see it, these are different cuts. So these are the areas that were removed from the brain. But I was saying I knew someone who did an experiment with HM, like basically, and it was something around eating or something. Like you would give him food and then they would go out and then come back and then give him more food and then he wouldn't know that he just ate. Like that's how like he couldn't really form those sorts of memories around, having experienced something. So he had normal short-term and procedural memory. Short-term memory meaning that, well, you could hold the conversation, right? As long as the conversation was ongoing, he could hold it, right? He had because in order to hold a conversation, you have to have short-term memory. You have to know what was the previous thing they said that you're processing. Like when someone tells a sentence, what happens to that input? Well, it goes to your sensory register, then it goes to your short-term memory, and then you process it, right? Not all of it goes to your long-term memory, obviously, because you're not going to remember verbatim what I said. A lot of it becomes abstract. So he had normal short-term and procedural memory. So short-term being, well, he could hold a conversation. Procedural being, he could learn new skills, right? Let's say playing piano. He could practice every day and then get better at it, but not have a memory of practicing, right? So you would forget that these sessions happen, but in an unconscious way, he would get better at this skill. However, sorry, he also had. How is that possible? So there is a dissociation. Yeah. So let's say an example of procedural memory. Let's say you want to. Yeah. So I'll give you another example, just for the sake of it. Let's say you want to become really good at playing dart or something. So every day you play, for 3 hours you're throwing dart, and I imagine after a few months you'll become really good at it. Right? That's the procedural memory, right? That's a skill that you've learned. Even even not remembering all those sessions that you practice doesn't matter. There's a memory, right, in your arm, in your brain, in your motor area, and you're probably this movement because there's plasticity in the brain. So a lot more neurons are probably now involved in this movement, right? And because of all of that, you become better at it. You don't have to have a memory of those sessions. Like in this extreme case, he wouldn't remember any of those sessions that he practiced, but that doesn't mean that he wouldn't get better at this skill. So that's the idea. So it's procedural memory that is getting better, but it's not. In this case, was actually he was able to Yes, I think yes.
Kind of also like memory.
Yeah, so yeah, so with instruments it's harder to see because it involves other knowledge too. Yeah, that's fair.
So he didn't have a problem with long-term memory, right?
No, no, that's so he had memories of, let's say, up to 2 years before the surgery. He had knowledge of those experiences, like places he has been, knowledge about himself, who he was, like that's part of our autobiographical memory, right? These are all declarative knowledge of the school I've been to, the cities I've traveled to. He had knowledge of those things, but now he could not form them anymore, right? It's about forming new long-term memories, like basically putting new traces in the brain of new memories. Um, that's the deficit. This is the deficit is in going from short-term memory to long-term memory, right? So if I experience something, if I eat something right now, like I had lunch, right? That was a short-term memory thing. The fact that I remember it now, that I recall that, that's part of long-term memory. The fact that what I ate, right? Where did I buy it from? All of those things, it's a consolidation into long-term memory. Yeah.
Is he aware of the fact that he could form long-term memories? Um,
I think that's a good question. I think he was aware of it to some extent. I think he was aware of it to some extent. Yeah. Yes. I see. Okay.
Every 10 minutes, what would happen?
I see. Okay.
Forget that boarding.
Mm.
But I wonder, like, for example, with his wife, he had a wife.
I don't know his life
Yeah,
history.
like, and I mean, I imagine he remembered his wife because he had.
Yeah,
some
I've
long-term
been
memory.
married before. Yeah.
But imagine after like 10 or 15 years, it changes a lot. Can you remember? You know what I mean?
These
Like,
are good questions. Yeah, I don't know. These are, yeah. Um, yeah, these are good questions. And I'm sure there is some middle ground in all of this, meaning that how much it was, how deep was the deficit and how bad it was. It's hard to tell, and I'm sure it got worse over time. So I guess plasticity depends on, so if 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 he didn't, so I guess the idea is that he didn't have the brain area to be able to consolidate memory, right? So you could experience something, but not be able to consolidate that into long-term memory. And that consolidation probably required, right, putting a place and a moment and a context together, right? We talked about binding, was it last or a couple of weeks ago, right? So when we talk about binding, um, there is a smaller problem of, or not, a different scale of bindings, right? There's binding of, let's say, features of one object together, but there is a binding of a moment to an experience, to a visual experience, when all of these things, for all of them to become one holistic experience. And I think that's the idea of what hippocampus does, right? It binds a sensory experience to a place, to a sense of self. And I think that was missing for him to be able to consolidate that. But the brain plasticity is not gone, right? His cortex is still plastic. He still can learn procedural memory. So is there a question back there? Yeah.
Just sorry, I guess I have not understood properly. Because long-term memory, you have the declarative memory and the non-declarative memory. I have understood that this person specifically could have like procedural memory, which is long-term, right?
Yeah.
So what was impaired was the declarative memory.
Yeah.
In a sense, the long term.
Yeah, so you're right. I'm using it more broadly here. You're right. So his problem was mostly about the declarative long-term memory. Basically, not being able to form new declarative memories like mental, and we talked about being mental images or being world knowledge, right? Like new knowledge about the world. Again, I don't know the extent of it. I didn't interact with the man, so I don't know the extent of how deep his problem was in terms of not being able to gather anything about, like, not it would be a constant state, or there were ways for him to get around it. It's hard to tell. Again, this is the problem with lesion studies. It's hard to get a sense of what the extent of it was. But it gave people some evidence of this specific area being a lot more involved in forming those declarative memories. We'll see. So
And then also like through of a place in the brain where you can actually use that you can use for long-term.
yeah, I think it shows you that this specific area is very important for forming those long-term declarative memories. Again, it's not so. Let's look at this study. This is a lesion study with non-human primate. Like, so what is the task here? The task is that you place a cue with a certain pattern on one of the two food holders. The door opens up. The monkey basically knows that the food would be underneath that, so they move that thing and then they get food. Now, there's a delay period. Then they put a different pattern and the cue. Now, this is delayed non-match to sample task, which means that the food next trial will be under a pattern that doesn't match the previous one. That's what it means. So when you study memory, people use a lot of delayed match to sample or non-match to sample. Match to sample means, well, what it means, if the sample matches, you get the reward. If the sample and non-match to sample means that the sample that doesn't match gives you the reward. That's the whole thing. Now in this case, they lesion this area. So they did a lot of experiments with different monkeys and lesion different areas. And they found out that only lesion in hippocampus did impact the performance, but not that strongly. It was only when they lesioned the hippocampus and the parahippocampal area, that basically the cortical area that feeds a lot of input to the hippocampus, it was only then that they saw a huge drop, right, in performance. In the case of HM, they removed a lot more than that. Like they removed a lot of parahippocampal place area, the hippocampus, and also the amygdala. Like they removed a lot. Yes. So.
I'm just a little confused about the task. So they asked the monkey to match if the monkey matched the cue that was displayed.
So initially, so imagine they place a pattern on one of the two things, or somebody is close to the switch, maybe hit it. Some things with that switch is up, I don't know. Thank you. So the task is initially they place a pattern on one of the food holders, and the monkey knows that, well, that's where the food is, if there is a single pattern. Now, next time, there are two patterns that each of them are covering one of the food holders. The reward is, because this is a non-match to sample, the reward is always under the pattern that doesn't match the previous one. So the monkey has to know, okay, what was the previous pattern look like that gave me reward? Now I'm going to go to the pattern that doesn't look like that. So that they have to have this long-term memory of that pattern that gave them reward. Yes.
Does it matter if they just do one hippocampi since it's the bilateral?
Yeah, so it has to be bilateral for you to see the damage.
Okay.
So a lot of time, so again, with HM, the problem was that they removed them from both sides. So that's why you see the severity to that degree. But if it's, I think if it's on the one side, again, brain can probably recover from that. Is there a question on it? Okay. So do you all understand what the task is? So it's a, again, you could, this is one way to run this task. Another way to run this task is that, well, you just show an image if you wanted to run a visual task. You show an image, you have some delay, you show another image. If the, you know, if that second image matches the first image, they have to press a button, for example. In the delayed non-matched sample, if the second image doesn't match the first image, they have to press a button. And if it's correct, if it matches what the experiment they intended, they get the reward. So a lot of those experiments, like delayed matched sample, there are examples. You can make it harder. You can make it like 2-back. So you show a pattern, you show an image, and then you show another. So one pattern, another pattern, another pattern. And this pattern has to match not the previous one, but the one that appears 2 steps ago. 3-back, 4-back. So you could make that task, the memory task, more difficult by doing that. This is the simplest case possible. You're saying if the pattern matches, go to the pattern that doesn't match the previous one. So just remember that much. And the lesions I was in restricted to hippocampus, do not produce as severe a form of amnesia as do lesions that include surrounding cortex. That's the finding of this study. Because there were some issues before, like initially when they lesioned it and they saw the deficit, they said, okay, it's all hippocampus. Then later on, people did a more careful study, and again, these brain areas are not like drawn out in front of you to lesion them. Like it's all very difficult process of knowing what you're lesioning. So and then when you do it more carefully, you'll see that just lesioning hippocampus is not enough. And in the case of HM, it was a lot more than that. Okay. So I guess you could think of these evidence somewhat giving you this sort of double dissociation. Again, some of you asked about it a little earlier, between implicit and explicit memory. Implicit being procedural, non-declarative, and explicit being declarative memory. And you could see that, well, middle temporal lobe kind of lesion causes impaired explicit memory, but it doesn't really impact perceptual memory that much, perceptual priming or other perceptual learning tasks. But when you have a lesion, for example, in one of the cortices that are sensory cortices, in this case, let's say visual cortex, it doesn't really impact your explicit memory, right? You still are the same person, and you have the same knowledge and can form new memories, but it really impairs perceptual priming, right? You can't really be primed that way and find association between visual input because your visual cortex is not working well. So it tells you, at least broadly speaking, there are different machineries that are underlying these things. But as I was saying, long-term memory, at least, for example, in the case of HM, you could see that a lot of older long-term declarative memories they had are still intact, in a sense that they could still report who they are, know their identity, have memories that are older of their past. So those must be stored somewhere that is not removed with the surgery. And people's idea is that, well, hippocampus kind of brings all of them together and then it stores them back in the cortex. So it's a loop that goes into hippocampus. Hippocampus kind of binds all these memories, pieces of memories together, make them coherent, and then it just kind of stores them back in the cortex. All right, let's look at an interesting topic. And these are what we call false memories. You may have heard of them. in this experiment, what they did, they took people's childhood photos and they placed them, in this case, in a hot air balloon, right? It's a picture of a kid with their father, and then they just put you in a hot air balloon. Then, so they have a little believable part, something that actually happened. This picture is real, but the whole context of this other thing is not real. Then they brought these people in and asked them questions. They were like, "Oh, remember that time we went on a hot air balloon thing?" And they were like, "No, I don't remember." They're like, "No, actually it happened. Oh, this is a picture of it." And then you show them the picture, and then they look at it and they're like, "Oh, you're right." Like almost, again, in the experiment, almost half of them start making up this whole story about how much fun they had. They went on this hot air balloon. Yeah, I think and then they kind of guess how old they were from here. They were like, "Oh, I must have been 5, 6 years old." Right? So it's not hard to plant memories in people's head, like, because this is like, because we have seen hot air balloons, like we've seen other people going on it. We have some images of what that looks like. It's just a matter of imagining yourself in that environment and imagine a believable part of that thing, and then you'll be like, "Oh yeah, like, so a lot of, again, this has a lot of implications for legal cases, right? Cases that are very old, like cases that people talk about something that happened 30 years ago, like 25 years ago, and it's hard to know how much of that is true. There must be something true to it. There may be something true to it, but you don't know how much of it is false memories that you just build around it because you're imagining yourself in certain situations. So this is very important in that case, in that context of, we do a lot of things, a lot of legal cases, court cases rely on eyewitness testimony. Not eyewitness testimony that happened yesterday. A lot of time, how long these court cases are, right? Eyewitness testimony of something that happens a few years ago, a decade ago, 2 decades ago. And it's really like, that's why a lot of time those sorts of claims don't hold cross-examination, because the story changes.
Identify someone, even long term. I mean, didn't happen 2 years ago, happened last year, and they plant a new memory that they are
Yeah.
confused. So it's very
Yeah. So yeah.
not so long.
Yeah, no, definitely. Even when it's not a far distant memory, you could, because you are in a different emotional state, right? You're a heightened emotional state when certain experiences happen, let's say a robbery or something. So you're very likely to not remember things correctly, right? You don't encode memory good when you're not in a calm, state, right? When you're studying, for example, it's much harder to retain when you're doing it last minute and you're stressed out and everything. So it's good to start early um, and do it, slowly, rather than trying to do everything in last minute. Exactly for that reason, because it's just much harder to retain memory when you're, in an emotional state. You could even inject people with something and change their, heart rate, and then they would have a hard time remembering the stuff later. So one thing about it, I gotta move, I have a few more slides we have to get through. So one thing about it is that when they put people in the scanners and they ask them these questions, something interesting is that memories that are real happen to have a bigger sensory component to them, right? Even when they describe those memories that are real happen to have more details to them, details that are correct, but also that they talk about the color of something or the smell of something. It's stuff that are not high level generated. So, and you could see that in the scanner, in a sense that you see activation in the sensory areas that are closer to the physical world than activation in the higher frontal areas. So this is something that they observed. Okay, so lateralization during encoding. Another thing is that even during encoding, there are different brain areas that could be involved depending of the type of information that you're encoding. This is like experiment, and I thought it would be interesting to include it. Is that when people are encoding words or they're encoding nameable objects or faces, they see different patterns of activation in the frontal areas. So even in this case, right, even encoding could go through different, different brain areas in the frontal lobe to become engaged in. Just something to know. All right. So now we talked about example I gave you with false memories in an example of long-term memory being kind of faulty. But alternatively, we know how good long-term memory is. We know how, it almost feels a limitless capacity that long-term memory has. In this experiment, the participant viewed pictures of 2,500 objects over 5 hours, 5.5 hours. Now, afterwards, they were shown pairs of images. Now, this pairing is kind of important. It's key to the experiment. If you show people pairs of images and ask them which one of them was actually in the data set, right? If you just show them one image and say, was this image in the 5.5 hours that you spent? That's a much harder task than when you show two different images and say, okay, which one of them was? And they pair the objects 3 different ways when they ask them which one of them was in there. One, they pair them with novel categories. So the categories that did not appear when they were doing the encoding. The exemplar, which is basically the same basic level category, so basically different mirrors, right? So you have this mirror. So here it means that, well, this denture or whatever this was in the data set, but this other category wasn't. Here it means that this mirror was in the 5.5 hours that they saw encoded, this mirror wasn't. Or you could go as far as this, where a piece of bread was just kind of misplaced a little bit, meaning that this one was in the encoded information, the number of the 2,500 images they saw, but this one wasn't. Can they say which one was or not? So you could see that this is really testing their memory on 3 different levels, on categorical level, on exemplar level, and on a very detailed in a different state or pose. So what they found is that people, so first of all, this is kind of reasonable, where you would be much better when you're given 2 objects. One of them is from a category that you did not see in the 2,500 images, versus when you see something that is in the same basic level category, like one remote control versus another remote control, or just a different state of the same object. But across the board, they were really accurate. They're like 87 to 93% accurate. So what does that mean? It means that there's really a huge capacity to their to their long-term visual memory. That when they looked at these images over the course of 5-6 hours, they retained something that when you show them 2 objects, in this case, that is the same, basically much the same object, but in a different state, they're able to say, okay, this was the one that I saw, or this was the one that I saw. So it tells you something, that their long-term visual memory is very detailed, that they remember details of everything very well. So this is just an example of an experiment. These are the type of experiments that are done in order to show how detailed and massive our long-term memory is, especially for visual input, right? Sometimes, you could remember details of things even with one exposure. Okay, yeah. So this is a challenge for models and our understanding of how is it that we're able to remember these things so well. So this is my last slide, and then I'll go through the two questions that I added. So dementia refers to a slow loss of cognitive functions and memory beyond what is expected from normal age, right? The normal aging, our memories get worse, you know, like many other things. But dementia really refers to cases where the worsening is way beyond like what would be a normal, considered a normal age. And Alzheimer's disease contributes to 60 to 70% of dementia cases. So, you know, we all have family members that suffer from it. It's really characterized, and again, the biological marker of it is aggregation of these proteins around the cell and around the connections between the cell that really limits their synaptic formation and also the neuroplasticity, right? For learning, we need plasticity. We need connections to be able to change for us to learn something, for us to retain something. And in this case, it really damages that process. The medial temporal lobe that we talked about is a structure that is first affected in this case, and but it also spreads to other areas. Vascular dementia is another version of it. In this case, it's basically oxygen not reaching the cells, kind of, and then cells are slowly dying. And this also affects multiple brain areas and also co-occurs with Alzheimer's disease. I just wanted you to have an understanding of what happens in these cases. Again, we don't have time to go into details of them, but that's what that is. On to the questions. We have time. So I added 2 questions. You've already gone through the first 8 questions. The TAs have gone through them, and you have the answers for them. Medial temporal lobe is an essential part of memory formation. Discuss one case of human and one case of non-human primate lesion-based experimental evidence for the function of this area. Okay, so what are those? These are the 2 experiments that I talked about. One in the context of a human, which is patient HM. You could talk about, well, patient HM had seizure, they removed his medial temporal lobe bilaterally, and he started having problems with declarative memory, evidenced by this, and that, but did not have a problem with procedural memory, evidenced by the fact that you could learn, you know, skills, right? So that's an example of you're saying, okay, what is the role of this area? The primate study is this one. You could describe this study as I did. It's in the recordings. I'm not going to repeat it. You could look at the recording and see how I described this study and discuss the fact that the lesion that was just targeted at hippocampus did impact the behavior, but the actual damage and problem arise when the lesion is spread outside of hippocampus to the cortical areas that feeded the input. So you could discuss this study. Just think about this study more and discuss it. The other question, we saw an example experiment showing how long-term memory can be faulty. And we also saw an example experiment of long-term memory having a massive capacity. Explain both of these experiments and their results. What are these experiments? Well, they're these experiments. This is an example of long-term memory being faulty. You could explain how false memories work. Again, this is an example. You could use another example. I don't particularly mind it. If you have read a paper where they discussed how they planted false memories, like there's another paper, for example, about how they would ask people, oh, remember when you got lost in a mall when you were a certain age? And then people would be like, oh, I don't remember. Yeah, it was a mall. And then you would tell them what the hometown was. And then as you add more true information, they somehow build up this story, this narrative around the true information and the fact that they were lost. So that's another experiment, but you have to go read the paper for it to discuss it. You could discuss this one. It's, explain how this experiment was done and explain what this means in terms of neural activity as I described it. I could share that. I don't have it here, but I could potentially share that later. I could also update these slides and put them somewhere up here and then share the new slides. This is an example of how people have shown generally that there is a massive capacity to long-term memory. And as I described this study, you could describe it too and show that, well, even to the extent that even when they had the same, type of food, but cut in a different way, people were able up to 87% accurate in terms of knowing which one of them actually appeared in their encoding, like which one of them was the one that they were supposed to maintain in the long-term memory. Yeah, I mean, it's in the recording, so you could just go listen to them again if you don't remember it, and form your answers. Yeah, and with the other questions, I'm basically always asking about experiments because I want you to think about in terms of experiments and how an experiment, formed around a hypothesis is testing it or not, or how do you, gain new knowledge with new experiments. So that's the type of questions I ask. Any questions? You all feel good about exam next week? Yeah.
Are there going to be any trick questions in the multiple choice, like the sky? Why is the sky blue?
I hope not. No, there won't be any. It's going to be all straightforward.